Okay, in this video, let's discuss Diffie-Hellman, DH in short, key algorithm. So this algorithm is used by two parties, say user X and user Y, if they want to create a shared secret key over an insecure channel. What I mean by this is, for example, we have user X, we have user Y, and they want to communicate with each other, let's say chat with each other. So, over that chat network, if they openly try to share plain text, their chat messages in plain text, that can easily be watched by an attacker and spoofed by an attacker, and they can gain access to those chat messages. Or if they try to create some sort of um, secret key, and then they try to encrypt their chat messages and then they try to do the chat. So if the attacker gains access to that secret key, then also it can the attacker can decrypt those messages and then again gain access to them. So this is where Diffie-Hellman key algorithm comes into play. Here each user generates and does some computations with few variables to finally arrive at a shared secret key, which will come to that. What are those variables in play over here? So let's take up an example um, and try to observe what is happening under the hood in this Diffie-Hellman algorithm. So let's say, so I have created this space. Um, I have segmented out spaces for user A, user B. So these are the private spaces of user A and user B, and consider this as the public space. Basically, the attacker can have a watch over here. Let's say my attacker is placed here, right? And they are watching in the public space. So everything that gets shared in public space, the attacker can gain access to that. Okay, let's say this is the attacker, right? So what this algorithm does is, we have some fixed values which can be easily accessed by the attacker, right? So we have a prime number P. Let's take currently the value as 13 for now. Then we have a generator G variable, and let's take its value as 6 for now. Okay. So what user A will do is, they will also have access to these fixed values over here, P and G, right? P and G. Okay. So these users will create a private value or key in their private space. So they won't share these private values or private keys to the public space. So you can try to consider it like user A can generate it on their device locally. Okay. So these are private value of A. So for example, let's say user generated a private value as 5, and similarly user B generated a private value of 4, for example. Okay. So according to this Diffie-Hellman algorithm, we compute the public key which will be shared by A and B. So public key is what gets shared over the network. Okay, if A and B want to communicate with each other. Okay, so this is computed by a formula of G variable to the power of the private, and then what we get, the number, will mod it with P. Okay, so the public key, this then gets shared over the network. Okay, so if we try to compute it for A, so we can see G is fixed, what we defined above under the fixed value, so it's 6. Then to the power of the private key of A. Now private key of A is not known to anyone except for A. So to the power of 5, and what we get, will mod it with 13. So if you try to compute this out, you will get the public key of A as 2. which can be shared, right? This can be shared. Okay. Similarly for B, if you check, you have G, which is a fixed value as 6, then to the power of private value of B, which is 4, which is not known to anyone except for B. Then what you get, you will mod it with P, which is again a fixed value, which is 13. So you get user B's public value as 9, which again can also be shared. Okay. So what's all the purpose of this? Let's see that in a bit. So now we have, so what you have for now, you have couple of values. You have P, which is a fixed value. You have G, which is a fixed value. And then you have couple of values for user A. So you have user A's private key as 5, which is only known to user A, or I might use UA below. Similarly, user A has a public value which got computed as 2, which we just computed above, and this can be easily shared. Okay. Similarly, for user B, you have a private key of 4. Okay. Again, this is only known to user B. And then a public key which gets shared, which we just computed above as 9. Okay. So these public keys are shared over the network as I just explained above, but private keys are not shared over the network and generally stay local to a user's device as we just discussed above. Now with Diffie-Hellman algo, user A and user B can reach to the same shared secret key without even exposing their private keys. So now this is where things get interesting, that we are saying that we have these couple of fixed values P and G. Okay. So what we'll take is we'll take P, we'll take G, we'll take public key of user A, we'll take public key of user B, and from all of this, using Diffie-Hellman algo, we'll try to come for both A and B, or user A and user B, to a shared secret key. Okay. So again, I am continuing with our earlier example. So we got to, as we saw above, we had a private value or a private key for A was 5. Then we reached its public value as 2. Similarly for B, we had it as 4. We reached a public key as 9. Similarly, this I have mentioned it over here. Okay. So this stays to the private space of user A, and these are the public values, so they can be easily shared over the network. So public keys are exchanged of both users who want to communicate with each other. Now what happens is, if let's say A wants to communicate with B, so A will use its private key and the public key of user B and will try to reach to a shared secret key, let's say S of A, and then with let me write private key of A plus public key of B using this. And similarly for user B, it will reach to a shared secret key of B using private key of B along with public key of A, as it wants to also communicate with A. Okay. And we'll eventually see that SA and SB, we would eventually get SA and SB as same. Okay. So what's the equation for that? So what we do is we have the shared public key, as I just saw above, with whom user A, for example, wants to communicate. So if they want to communicate with user B, okay, so here we take up the shared public key of user B, then the private key of user A, And then again we mod with the fixed value, which was p, which we defined above. And this is done at their own sites, at their own private spaces. So if we see, the shared key for user A becomes shared public key of user B if it wants to interact with B, with private key of A itself, then the mod with P. And similarly for B, this becomes if it wants to interact with A, so shared public key of user A, then the private key of B itself, and mod with P. So if we try to plug in the values, we saw shared public key of B was 9 and A was 2. So we plug in 9 and 2 with respect to their own private keys, and then modulo with fixed value, which is 13, which we defined above. If you go at the top, you can see private P. So P's value was 13. Okay. So if you compute this, you will reach to this, let's say, have S of A, and this comes out to be S of B, and you can see both are same, and these get computed at their own ends, gets computed at their own user A and user B's secret spaces or private spaces, without ever exposing even these shared secret keys as well. So both users reach the same shared secret key without even sharing their private keys over an unsecured network. So under the hood, it uses discrete logarithm concept. Let's say someone is spoofing in the unsecured network. What all things do they have access to? So let's say, as we saw above, we had an attacker, okay, sitting at the public space and watching that unsecured network, these two users talking to each other. Okay, so what all things the attacker can have access to? They can have access to the fixed values, which is the P, the generator value G. Then they can also have access to the public key which was shared by user A and public key which was shared by user B, not their private keys, or eventually the shared secret keys which they computed. But attacker doesn't know about private key of user A and user B, as I just mentioned. So as we saw above, we had an equation to compute the public key. Okay, what we did is G was a fixed value, P was a fixed value, and private value was never exposed. So for example, for user A's public key computation, we did G to the power of private key of user A, and then whatever value we got, we did a mod with P. Okay, so let's say our attacker is here. So what attacker can see? Public key of user A, G, and then P, and not this one. They can't have a watch on the private key of user A, as it was local to the user A device itself. Now this is where things get interesting and pretty much difficult. So to get the private key of user A, this becomes eventually computationally infeasible for the attacker as we keep on increasing our value of P. Okay, so let's take up some example. So what attacker gets access to? For example, we have a value of P is equal to 23, G is equal to 5, and let's say public key of A was 8. An attacker has access to all these things, but not the private key of user A. So let's consider this as the private key of user A, which is local to its device. Okay, so we, after plugging in these values in G to the power of private key of user A, what we get, we do mod with P, we get the public key of user A. So basically, if you check, so public key of A was 8, so this is 8, this is what attacker has access to. Then mod with P, so mod with 23, and then G to the power of private key of user A, so 5, this also attacker had access to. So this becomes 5 to the, so what if attacker with all these values now trying to reach, let's say via brute force, trying to guess and reach till the value of the private key of user A or UA. So what will become is, we'll get 5 to the power of UA is equal to 8 mod 23, and then UA becomes log 8 to the base 5 mod 23. Now if you see, this is what we call discrete logarithm. So generally in Diffie-Hellman algo, as we keep on increasing the value of p, this becomes computationally impossible to reach and guess till the value of the private key of user A. So generally in Diffie-Hellman algorithm, we take very large value of p, say 2 to the power 2048, and the private key of user A may reach to, with this 2 to the power 256. So if the attacker even keep brute forcing till it reaches that sort of value range, it would require sort of 2 to the power 256 operations, which becomes sort of like computationally impossible. Hence, this concept is also used in banking, end-to-end encryption of chats, crypto wallets like Bitcoin and all these sort of places.